Hi all, you should have the worksheet for these three examples. If not, make sure you go up to the website and grab it off the schedule. What I want to do is I want to talk through these three. Just give you three more examples of rational functions to follow through, take some notes on, and then you should be set to work on these as well. Here we're supposed to sketch the graph of f of x is equal to 2x minus 8 over 4x squared minus 64. Label all discontinuities, give the domain a range. First things first, remember we need to factor this out. Always go after your greatest common factors first. So I have 2x minus 8, 4x squared minus 64. So I can pull a 2 out of the top and a 4 out of the bottom. And then from there you should be able to factor out the bottom some more. Now, of course, if you were a good, awesome student, you would have already paused and done it yourself, but that's all right. And then what we need to mess with here is we're going to list out parts. So like here, what's your domain? And so your domain right now, x cannot equal negative 4, x cannot equal 4 based upon what's going on here down in the bottom. Okay, so this is all coming from here. And then over here, well, first of all, so from over here, then let's talk about the simplified version. So the simplified version of the function, you can divide out the x minus 8 or the x minus 4. So those are going to go away. So your simplified version, and actually the 2's are going to divide out. That'll become a 1. That'll become a 2. So your simplified version is going to be 1 over 2 times x plus 4. So that's going to be the function that's going to mimic what the original function is, with the exception of what the discontinuities are. Down over here, let's list out what your vertical asymptote is. First of all, we're going to have a vertical asymptote. Remember, that's from where this function is. Vertical asymptote always comes from the basic function here. Your removable is going to be coming from what got removed out of when you simplified. So your vertical asymptote is going to be at x equals negative 4, since that's what's left over. You're going to have a removable one at x equals 4. And then lastly, you've got your horizontal asymptote. And that's always going to be obviously a horizontal line. And that's going to be what happens when x goes to infinity. So as x is the end behavior, remember. So as x gets really, really large, you're going to have 1 divided by a larger and larger number. So that means that y is going to equal 0 is going to be that. And I do have some examples where that's not going to necessarily be the case. We'll go different, but we'll start off simple. So first of all, let's draw in your asymptotes. So you have an asymptote at x equals negative 4 there. And we've got our horizontal asymptote here. So all the action, remember, is going to happen around that asymptote, the vertical asymptote. And so what you're going to end up doing is you're going to end up plugging in numbers on your chart or from your table, or however you want to do it, around that. So effectively what we've got then is you put your vertical asymptote in the middle, so it's going to be negative 4. I don't have anything there because it doesn't exist. And then negative 5, negative 6, negative 3, negative 2, and plug those numbers in and see what you get. So if I plug in a negative 5, I'm going to come up with a negative 1/2. If I plug in negative 6, I'm going to come up with a negative 1/4. If I plug in a negative 3, and again, and you're using the simplified equation up here. If you plug in negative 3, I'm going to get 1/2 and 1/4. Now the only reason why you're getting this kind of symmetry between the two is because you have a horizontal asymptote at 0. If that gets moved, then obviously you're still going to see some symmetry, except that it's going to be in relationship to the horizontal axis, or horizontal asymptote. So at negative 5, we're right about, actually here, let's do this. Well, okay, so we've got about 1/2 here, 1/4, and that's going to keep on getting smaller. So that means that this is going to be on the negative side. Now the other thing to remember is that over here, don't forget that we have the removable discontinuity, so that the removable discontinuity is over here somewhere at negative or at positive 4. So when we come down and draw this, we need to make sure that we include that. Remember, the points are important instead of just kind of freehanding it in, so then that way we can make sure we get the scale right. How close is it into the corner? If we didn't have the 2 in the denominator, this would be up higher, like, okay, this would actually be up higher and be going through like something like that. And that's important, so you need to make sure you get the stuff right. Okay, so domain and range. Now, so your domain, we've already kind of messed with. So let's formally say this. So my domain is x such that x cannot equal 4, x cannot equal negative 4. My range, what's that going to be? Oops, I forgot to label my axes. Your range is such that f of x cannot equal 0. It's that horizontal asymptote. And sometimes you'll actually have values of the horizontal asymptote, but that's what we've got for that one. Okay? So if you flip your paper over, before you get started on that one, there is one mistake I need to correct. And that should be, this should be a 6. So x squared minus 6x minus 27. So again, factor this out, and I want you to fill out this chart first. So go ahead and pause this after we set this up initially. So I want you to list out what your domain is, what is a vertical asymptote, what is a removable discontinuity, obviously what's the simplified version, and where your horizontal asymptote would be. So hit pause, kick through that, and I'll see you in a minute. All right, so your horizontal, or excuse me, before you do that, the simplified version, first of all, we have to factor this. So I've got x plus 4 over the quantity x minus 9, x plus 3. So the simplified version is actually just what we already have. There's nothing that divides out. And so your domain is going to be, actually, let's just go ahead and be formula here. X such that x cannot equal 9, x cannot equal negative 3. So my vertical asymptotes are going to be at x equals 9, x equals negative 3, and we have no removable discontinuities. Because nothing divides out when we simplify this. Now your horizontal asymptote, what you're going to do when you have variables on the top is you're going to look for the largest degree. You're going to take the highest degree term in the numerator, which is x, and you're going to take the highest degree term in the denominator, which is x squared, and you're going to reduce that. So now, when you look at that, when x goes to infinity, what does the function do? The function goes to 0. And sometimes that'll be something such like, you know, if I had x squared in the top, then it would be going to 1, and you draw it there. So anyway, so we've got two sets of vertical discontinuity, or vertical asymptotes here. So we're going to draw both of those in. So I have one over here at 9. Actually, you know what? I'm going to cut this in half. We're going to count by 2's here, at least on the x-axis. So this is 10. That's negative 10. And then label your axes, Mr. Hayes. Just nobody likes somebody who doesn't do that. And then we've got one over at negative 3, so we'll draw that in. And then all the points that we're going to pick, oh, and then the horizontal asymptote. And then from there, you're going to pick points. And again, now in this case, since we have two vertical asymptotes, you're going to be picking out two sets of points to graph around. So in this case, for the first one, I'm going to center it around -3. So -3 doesn't exist, so we go there. I have -4, -5, -2, -1. So you're going to plug those into the equation. So you get -1 over -14 times -2, so that's over 28. If I plug in a 4, I get 0. Over it doesn't matter. But since it matters to some of you, it's going to be what, -13 times 1 instead of 13. Horizontal asymptotes are the places where the end behavior goes. You can actually touch those, so that's the time when your little brother, remember we talked about the little brother theorem about you get infinitely close, but it's the I'm not touching you thing. Well, occasionally it happens, and that's what happens here. And then on the other side, for -2, I get a +2 on the top, and then I get a -11 times 1, so -11 there. And then on the top, I get 3 over -10 times 2, -20. So let's plot this part out first, because we can at least do it with the left side. On the left side, so we've got something that's really, really close to 0 at 4. Actually, it is 0 at 4, and we go down below. And what that tells us is that it actually is going up. So it's starting, and now we know end behavior is going to start around 0, so it's going to be on the negative side of 0 down here. And it's going to go up and pass through here and go straight up. And usually the further the asymptotes are apart, the more extreme you get in terms of how fast these things spike up and down. To the right of that first vertical asymptote, so you've got, this is approximately what, just underneath. Again, really, really close to 0 on both of these again. So you've got like 2, actually here, if you look at your table, you can kind of get a sense of what's going on. It's not a bad idea to plot a couple of points in between if you've got a big space like this. But so you've got numbers really, really close to 0, but notice that they are negative. Okay. And then as we get closer to the 9, of course, is where everything goes. It starts to spike down. And so this graph, it's obviously much steeper than a parabola. A lot of people try to say, oh, it's a parabola. No, it's not a parabola. And then on the last one, you've got positive numbers. So like when you hit number 10, you're just bigger than 1. And then it starts coming down like this. Please make sure you have arrows on both ends of these, because these do continue on forever. Okay, and so then that would be what the second one looks like. So if you have 2 vertical, and again, it depends on how many times each of the asymptotes happens, because again, you can have multiplicities of more than one, which we'll deal with in the coming days. But that at least gives you an idea of what happens when you have 2 vertical discontinuities, and then what it looks like. So sometimes you'll pass through your horizontal asymptote. It's just kind of one of those anomaly things. All right, let's take a look at one last one. Last one on the sheet that you have. And again, go ahead and take some time to factor this out, see what happens. So hit pause, come up with the box yourself, fill that out, and then compare your answer to what we have here. All right, so hopefully that didn't take too long. So we have our domain up here. And again, if we have this thing factored out, I've got what, 2x and x, and then a minus or plus 4 and minus 3 all over x plus 4. So to simplify, so first of all, for the domain, it's x such that x can't equal -4. And then for the simplified version, you get 2x minus 3. So what did you come up with vertical asymptotes and removals? So for my vertical asymptote is at none. You don't have one. It goes away. All we have here is removable discontinuity. And that removable discontinuity is at... Now here's the interesting thing. Since you have removable discontinuity at x equals -4, what you can do, which is really kind of cool, is I can plug that into the simplified function. So I can go 2 times negative 4 minus 3, so that's going to equal negative 11. So you have this, so you've got this removable discontinuity at negative 4, negative 11. Because this simplified version, of course, is a line, so it should be pretty easy to grasp. And for your horizontal asymptote, same thing. It's not going to be, there's going to be none. Because as x goes to infinity, the function goes to infinity. So, interesting stuff, isn't it? All right, so let's plot this thing out. Now, since your simplified version is not a rational, it's a linear equation, you're going to graph it like you would a linear equation. Now, the only thing that we need to do here is, since that a removable discontinuity is actually off like what would be in base a normal negative 10 to 10 graph, is that we're going to, again, much like we did the last one, modify the scale a touch. So my function axis is going to count by 2's. My regular function axis is going to go ahead and count by 1's. So your y-intercept is here at negative 3. It's going to go up 2 over 1, up 2 over 1, up 2 over 1, etc. And then remember, over here at negative 4, I'm going to be down here at negative 11, and you can have an open circle here. And then from there, you are going to draw a straight line, and that is what that rational function looks like. People usually like those because they're much easier. You don't have to mess with things. Okay? So those are 3 examples for you to use for your models for some of your homework. I hope that helps. As I said, we're going to spend another day or 2 on this in class, so we'll have some time to decompress some of this. But you've got some good, solid examples there for you. So I'll see you tomorrow. Hang in there. As always, call, text, email if you guys have questions.